Hello again, physics friends. Today we're going to focus on actual real-life particles and not just trains going near the speed of light. So we're going to turn our attention to a fundamental particle called the muon, which often is abbreviated with the Greek letter mu for a symbol. And what do we need to know about a muon? Well, we need to know that it's a fundamental particle that's produced in the upper atmosphere when cosmic rays smash into our particles in our atmosphere. They produce showers of other particles, including neutrinos, pions, and so on. And the muon particles are long-lived enough to make it all the way to sea level, so that detectors in laboratories at sea level can count the number of muons coming through. Now, for those who haven't heard of a muon before, all you really need to know about that is it's essentially an electron, only about 200 times as massive, and also unstable. So it decays into an electron. So a muon is like, it's like the heavier cousin of the electron. Okay. And there's positively charged muons and negatively charged muons, just like there's positively charged electrons and negatively charged electrons. But a muon is unstable. So a muon particle, if left alone, after some time, will decay into an electron and other particles like neutrinos. So the muon decays with a typical lifetime of about 2 microseconds. Okay. Now, what does a lifetime of 2 microseconds mean? It does not mean that after 2 microseconds a muon will decay. Right? The decay is a random process, and a characteristic lifetime is 2 microseconds. So some muons will decay on shorter times than that. Some can live longer than that, but a typical kind of representative value for the lifetime of the muon is 2 microseconds. Now, mathematically, when we say the lifetime, what we're talking about is if we think of the number of muons as a function of time, we can write that as the number of muons to begin with, and not, multiplied by an exponential function, t over e to the minus t over tau, and tau is called the lifetime. So if we were to draw a graph of the number of muons versus time, we start at t equals 0, and if we put in t equals 0 to this exponential, we have e to the 0, so that's 1, and that means we're starting at time equals 0 with a number of particles, number of muons n naught, and this function is an exponentially decaying function, like so, and after one lifetime, about 63% of the muons will have decayed away, which leaves 37% of the number of particles that we started with. Okay, and one way to see that is if we plug in a time that's equal to one lifetime into our equation, we have n naught e to the minus tau over tau, which is n naught e to the minus 1. And if you raise e to the minus 1 power, that ends up being 0.37 n naught. Okay. So the lifetime is sort of like a half-life. In fact, it's related to the half-life. The half-life is the lifetime times the natural log of 2, which you could show in a pretty straightforward calculation. But basically think of after every, if as a time equal to one lifetime elapses, you lose about 63% of however much you had. And that process continues and continues and continues. So roughly speaking, every 2 microseconds, 63% of your muons will decay away on average. Okay, so these muons, which are produced in the upper atmosphere, provide us with a way to test relativity because these are particles that vanish or decay into electrons after a certain amount of time, and that time ends up being comparable to the travel time from the upper atmosphere where they're made down to sea level. So there's actually a great experiment that was done in the 60s, and I will link to that video on the course website that goes into this experiment in much more detail. But we basically do a test where, the scientists did a test where they measure the number of muons at sea level and compare it to the number of muons on the top of a mountain. So for example, like imagine this being a mountain. And down here we have sea level, okay? And we have a detector that's located at the top of the mountain. We'll call that detector 1. Okay, and then down at sea level we have another detector. And in come these muons that are moving at relativistic speeds. So here's the muon moving at high speed. And we're going to count the number of muons at the top of the mountain, and we're going to count the number of muons down at sea level, and we're going to compare them. Okay. This experiment was done on Mount Washington. And on Mount Washington, the mountain has a rest length of about 2,000 meters. Okay, so we have two detectors separated by about 2,000 meters. The muons have a range of speeds, but a typical value for the velocity of the muon is, we'll use a velocity of 0.994 times the speed of light. So these are very relativistic particles moving near the speed of light. And so we could ask the question, okay, how long does it take for a particle moving this close to the speed of light to travel 2,000 meters? And we'll turn once again to time elapsed is distance divided by speed. Here we have a distance of 2,000 meters, and we have a speed of 0.994 c, and c is 3 times 10 to the 8 meters per second. And we can play this game out, and what we find is that the elapsed time is about 6.7 microseconds. Okay? So the main conclusion here is that it takes many lifetimes, about 3 lifetimes, where this Greek letter tau is the symbol we use for the lifetime. So this is about 3 lifetimes, as measured in the Earth frame, for these muons to go from mountaintop to sea level. Now remember, 3 lifetimes, if we come back to this graph, right, we saw that after 1 lifetime, we've lost 67%. And if you play this out, you go 2 lifetimes, 3 lifetimes. Well, at 3 lifetimes, we don't expect to have much at all. In fact, after 3 lifetimes, we should expect about 5% of our muons to remain. So expect very few muons at sea level compared to at the top of the mountain, and we expect that by few we mean about 5% or so to survive the trip. Okay, so we have a prediction, and that prediction is at sea level we expect about only 1 in 20 of the muons that are at the mountaintop to survive the trip. But when you actually go and make this measurement, what you find is that the number at sea level is essentially the same as the number at the top of the mountain. Okay, so that is an outcome that is not consistent with this idea that 3 lifetimes have elapsed for the muon. Okay, so this is a big discrepancy, and the question is, well, why is there a big discrepancy? And not surprisingly, since this is a course on relativity, the answer probably has to do with relativity. So let's see exactly what's going on. So we're going to tackle how to solve this muon mystery, and we're going to do it in 2 ways. The first way we're going to do it is by working in the Earth's frame of reference, and then after we understand the resolution of this seeming paradox from the Earth frame of reference, we'll redo the analysis from the muons frame, and we should arrive at the same result. Okay, so what did we find? We saw that in the Earth's frame, let's say we have we let our clock start at 0, right? Both of these clocks are at rest, so they're going to have the same reading. What we said was that 6.7 microseconds later, the muon will have reached sea level, right? So the muon's coming from high up in the atmosphere. It reaches the first detector at the top of the mountain. That is when our clocks read 0, and then the muon travels down, 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 down. 6.7 microseconds later, the muon reaches sea level. Okay. And the argument that we made, which turns out to be problematic, is that 6.7 microseconds have elapsed on our clock. That's roughly 3 lifetimes for the muon, so most of those muons will have decayed. But the problem with that argument, as you almost certainly readily figured out when I said it the first time, is that the muon is in motion. Okay, so the muon is moving at high speed. Okay, so its clock runs slow. Right? And specifically, we know that time dilation tells us how slow. It tells us delta t moving is less than delta t at rest, and it's less by this factor of gamma. Okay. Well, here the clock at rest is the Earth clock, and the moving clock is the muon's clock. Okay. Delta t Earth is that 6.7 microseconds that has elapsed on the clocks at rest. So we only need to know what gamma is, okay? So here we have to do some calculation for V is 0.994 C. We got to find gamma. Okay, so we do this by gamma is 1 over the square root of 1 minus V squared over C squared. And for V over C, we have 0.994. And we have to square that. And when you play that game all the way out to completion, you find that gamma is a little more than 9. So it's about 9.1, okay, which is very interesting. That tells us that although 6.7 microseconds have elapsed on the Earth clock, delta t on the muon's clock is almost 10 times less, okay? So instead of 6.7 microseconds having ticked off, we get a much smaller number of about just under 3/4 of 1 microsecond, okay, which is less than half of a lifetime. Okay, so here this moving clock has ticked slowly by a factor of 9. So if we look at this graph of number of muons as a function of time, starting with the number at the top of the mountain and decaying away over time. Remember, 1 lifetime is down here, and that's 2.2 microseconds, call it 2 microseconds. We're sitting down at 0.74 microseconds, so that's like here. And so the vast majority of the muons are still alive, okay? So we expect very few muons to decay. In fact, we expect this number, if we can actually calculate it, we'll say number at 0.74 microseconds is equal to n naught e to the minus 0.74 over 2.2, which is the lifetime in microseconds. Okay, and when we play that out, what do we find? Well, I calculate that that's about 70%. Well, I shouldn't use percent there, I guess, since we're doing a decimal. I'll write that as roughly 70% of the original number are still alive by the time they make it to sea level. Okay. So instead of having 1 out of every 20 survive the trip, we have 7 out of every 10 surviving the trip. And so if we do this experiment, we expect to see a very large number of muons at sea level. And the explanation, once again, to summarize, is that in the Earth frame, the muon's clock is ticking slowly because it's moving at high speed through the Earth frame. Okay, and so this idea of time dilation, it does not just apply to light clocks or wristwatches. Everything that depends on time, all of those processes that depend on time will be affected. And the lifetime is a process that depends on time. And so this muon will not decay when 2.2 microseconds elapse in the Earth frame. It will decay on average when 2.2 microseconds will elapse on the muon's frame. And that clock is running nearly 10 times slower than the Earth clock. So that's part one, understanding why so many muons actually survive the trip as interpreted in the Earth frame. So the next thing I want to do is look at the view from the muon's point of view. Okay, so we'll pause here and redraw the system in the muon's frame. Okay, so now we are mentally switching from the Earth frame into the muon frame. And in the muon frame, the muon's at rest, and the mountain, the detectors, and the ground are rushing up towards the muon at very high speed. Now, if we're going to do this correctly, and we hope to, we have to account for all of the known effects, right? So the first effect that we need to account for is the fact that the height of the mountain is no longer 2,000 meters, but it's shorter, it's contracted by that factor of gamma. And with a gamma factor of about 9, that tells us that the length ends up being close to 200 meters. It's 2,000 meters over 9.1, which ends up being about 220 meters. So if you were the muon, you would say, I see a mountain rushing towards me. That mountain is 220 meters tall. When the tip of the mountain reaches me, sea level is only 220 meters away, and at sometime later, sea level will have arrived at me. And when that happens, we would have the following picture, where the muon hasn't moved, and I'm indicating constant position with this horizontal dashed line, but now sea level has rushed up and has arrived at me, the muon. Okay. We also should recognize that these two clocks, or the clocks at each detector, are not in sync because the sea level clock is the rear clock. So if this mountaintop clock reads 0, the sea level clock will be set ahead. Okay. For this purpose, though, that's not so critical. Okay, so one question that we might ask is, okay, let's say that the muon has a clock, this internal clock that keeps track of when it needs to decay. It's going to start at 0, and then the question is, okay, well, what is the reading on this clock when sea level arrives? Okay. In other words, what is the elapsed time in the muon frame between these two diagrams, namely between when mountaintop arrives and when sea level arrives? How much elapsed time is that? Well, it's the time is given by the distance that sea level travels to reach the muon, divided by the speed of sea level. And by here, I mean the detector at sea level. Okay, well, the distance it has to travel that's the L naught over gamma, okay, the height of the mountain. And the speed that it's traveling is v, the velocity in the problem. And we already calculated that L naught over gamma is 220 meters. And we said that the velocity is 0.994 times the speed of light. And when you put in 3 times 10 to the 8 meters per second for the speed of light, and you carry this calculation out, you find that it takes 0.74 microseconds for sea level to arrive. Well, that's exactly what we saw when we did this solution in part 1 in the Earth frame. We found that it took about 0.74 microseconds for the muon to reach, on the muon clock, for the muon to reach sea level. And so what we have here is we can put in the 0.74 microseconds into the muons clock, okay? And that tells us that far less than 1 lifetime has transpired on the muons clock, so we expect most muons to survive the trip. And we already calculated that was about 70% of the muons to survive. Okay, and so that's how we see why muons reach sea level as analyzed in both the Earth frame and also in the muon frame, and we're finding the same result in both cases.